Hello and welcome to a quick talk about the Libre-SOC Power ISA core. What I'm going to be doing here is I'm going to be talking about what we've achieved so far, then where we would like to go, and then where we are present and the current plans, and from there the next steps that we'll be taking. So what we've got already is we put together something called, we called it Test Issuer. It was done very, very quickly with implementations of pipelined instructions divided cleanly according to their register profiles. So anything that used similar registers. So, for example, the condition register pipeline takes in register A and 3 different condition registers, and it outputs RT and 1 condition register. So that was its profile. Ended up with any instructions that used pretty much those registers, and likewise we ended up with an ALU pipeline and a logical pipeline and a multiply pipeline. So basically we planned ahead for a superscalar architecture, but then threw it together behind a finite state machine with an instruction per clock of about 0.1, very similar to Pico RV32. And this is just purely practical reasons of time. The idea was we had the opportunity to create a test chip, and the team had never done an ASIC before. But what was particularly significant is we did not use proprietary tools. It was entirely done using Libre licensed VLSI layout tools, Coriolis 2 from Sorbonne University. So it turned out to be 30 square millimeters and 130,000 cells with 800,000 transistors. Ultimately, we implemented in effect the compliancy level SFS, which is integer only, but we did it in 64-bit, and it included little engine per 64 and big engine per PPC 64LE and BE. Turns out that actually implementing big N, because the power instruction set already has byte reverse load and store, adding big engine is really simple. You just put an exclusive OR of the MSR.LE bit into your load and store. It's really easy. I don't know what the fuss is about. Obviously, we can't do big engine, because big engine is dead. It was like, it's real simple. So the other thing we've done, and this is a big piece of work on its own, is we've created an IEEE 754 pipeline. That says 764. It should be 754. I'll update the slides later. Now we've got floating point, add, mul. We've also got square roots and div and reciprocal square root. Div, square root, and reciprocal square root are actually in the same pipeline because they use pretty much exactly the same math and concept. We haven't done the version, the Newton-Raphson approximation version. We've done it as actual pipelines. And the reason for that is because when you're doing things for GPU, you need guaranteed completion time from guaranteed completion behavior for 3D workloads, and without that, you're very much hosed. You end up with div operations in your inner loops, very tight loops. So we did it as pipeline. And we've also implemented Cordic, which is really neat algorithm. It's long. It's similar to binary-based long division, so consequently it only uses add and subtract. But when you start adding in complex numbers into it as well, it produces sine and cosine simultaneously, which is particularly interesting. But it can also do measurements of the distance round an arc given the angle and the radius, which is quite fascinating, and a whole stack of other things. So it's not as optimal as many 3D versions of sine and cosine and atan, etc., which tend to use quadratic equations and polynomials approximation, etc., which turns out to be very, very good in FP32. Very area efficient. It's nowhere near as efficient as that, but the sheer comprehensiveness of the things is actually worthwhile keeping it around as an actual Cordic-based instruction and thing. So we'll consider that. Anyway, so that was a lot of work that has gone into that, but we just didn't have time to integrate it into the test ASIC, because we have to finish off the exceptions and the rounding to be compliant with the power ISA. It's parameterized because it's in Namigen. Namigen, you can pass in Python parameters. It's object oriented. So we have FP16, FP32, and FP64. And I'm really not kidding. There are well over 500,000 unit tests. It takes something like 3 to 4 days to run the unit tests on that IEEE 754 pipeline code. We've also created a dynamically partitionable SIMD infrastructure. Again, this is using the Namigen, which, by the way, is trademarked now by MLabs. And Libre-SOC, and the Libre-SOC is now the authorized maintainer of Namigen under license. So we'll be putting in some advanced features over the next months and years into Namigen, and one of those is this dynamic partitional SIMD infrastructure. Now, I've done some talks about this before. The typical way that you would do SIMD would be a for loop, an if statement. If you want 1 times 64, then do this HDL. Else, if you want 2 times 32, then do literally a for loop in your HDL around two different adds. Else, if you want 4 by 16, then you do a for loop in the HDL of four adds. Else, if you imagine your entire pipelined architecture having multiple repeated copies of your HDL in your pipeline, it becomes a complete total maintenance nightmare. The other way is to actually design your HDL explicitly so that it's subdivided down, so that even the most basic add operation has a hyper-specialist ALU, which explicitly opens up the gates between the add partitions and basically uses carry rollover to a different between the eight. Usually, your base unit would be eight adds, and you have a carry rollover. And all you need to do to create a dynamic partition SIMD is, if you want 4 times 16, well, in all of the odd carries roll over and add to the even 8-bit carries. And you can see quickly how that would extend up all to 2 times 32 and ultimately to 1 times 64. But then what we did in the dynamic partitioned symmetry infrastructure is to do that, but to hide it behind a standard Python add operator. And then we covered everything else, greater than, less than, etc., shift, and so on. So what we've also got is thousands of unit tests at every level. It's a thing. So we don't just have system level integration unit tests once the entire HDL has been completed. We have low-level modules which get their own unit test. And then when those are used in a pipeline, the pipeline gets a unit test. Then when the pipeline is used to create a function unit, the function unit gets a unit test. When we're testing the core, which puts all the function units, the pipelines together with a register file, where the register file had its own unit test as well, back down in its levels, the core gets its own unit test. And then when we add an instruction issue to finally create a final top-level core, then you can run all of the unit tests amalgamated below all those levels again and again. So we end up actually with 4 different ways of running the exact same unit tests to make sure that everything's still functional. So in order to make sure that we could actually see what the heck was going on, we needed a simulator so that we could do side-by-side simulations and learn about the actual power ISA as well. And so, but what the absolutely last thing we wanted to do was, having looked at the PDF specification and saw that we needed to implement 200 instructions, there was no way we're going to type that out by hand. So what we did was we literally took the PDF, the Power ISA PDF, did a process of extracting the pseudocode from the actual PDF specification, made it machine readable and made it executable by creating a Python, a compiler in Python, which turned that code, that pseudocode, into actual executable Python. And this allowed us to both learn about the Power ISA and actually to implement it. But if we found a mistake, then we knew that that mistake was most likely in the actual specification, not in our implementation. Turns out that there are actually some mistakes in the Power spec, or ambiguities that needed to be sorted out. So that's what we did. Then, as this advanced, and we added an MMU and level 1 caches, we had to actually add a Radix MMU to the simulator, and that we used the Gem 5 Power Gem 5 source code and QEMU's Radix MMU source code as reference, as well as the Microwatt HDL, Microwatt VLSI. So that's the thing. Then we could run those unit tests side by side with the HDL, single step the core, single step the simulator, extract the register file, compare them, extract the memory, compare that, and if mistake, if error, report it. So in this way, we went literally from the specification to a simulator based on the specification to HDL, which was accurate to the spec. Right. So what we've also got is we have a basic implementation of drafts SVP64. SVP64, which you can find out about online on the other talks and on the Libre-SOC website. But it is basically Cray-style vectors for OpenPOWER. And it is based around the concept of adding a for loop around scalar instructions. We do not add any vector instructions. We have added a for loop, a sub-program counter around the scalar power ISA. Okay, that is very, very significant. Right, and it's a concept that was actually Peter Hsu of MIPS back in 1994, when he was working on the MIPS R8000, actually came up with the exact same concept, that you have a prefix indicating that you want registers to be marked as scalar or vector, your source, individual source or destination registers, RA, RB, RC, RS, RT. You want to mark those as scalar or vector and then do this for loop incrementing through them. So it is not we're not the first people to come up with this idea, which is quite fascinating. But first to introduce it to a modern supercomputing ISA. So I have a huge number of demos of this, including in-place matrix multiply and in-place FFT and DCT. Now, the discrete cosine transform implementation, even I was astounded. It is in place. Most discrete cosine transform vector implementations, they're awful. They use double the number of registers that the equivalent FFT or discrete Fourier transform does, because of the swapping of the order of the top of one half of the registers is order inverted. And this is something that SIMD instructions cannot cope with unless you actually have an inverted order thing. And of course, that's I decided that wasn't good enough, and in SVP64 that it didn't have that, so I added it. But more than that, I added something that the research that I did, it turned out to that the ordering uses gray encoding, which is quite stunning. It's actually a really interesting mathematical discovery in its own right. But the thing is that no standard SIMD architecture would ever consider doing this, simply would not have come up with it. It's quite really interesting, but the basic principle, the closest other processors in the world similar to what the FFT and DFT does in SVP64 are the Qualcomm Hexagon DSP, which has the ability to group, I think, up to 20 instructions into a zero overhead loop, where you could, one of those is a decrement counter, and the others are the actual multiply and accumulate associated with the FFT, and the other ones are load and store, obviously. So we've done something similar to that. I won't go into detail now because it's quite. You can find the talks about it online and the details about it in the specification, the draft specification. The other one is the Texas Instruments DSPs, TMS 320 series, etc., which again they have. It's a VLIW-like instruction set where you can put up to 14 instructions, primitive instructions, into one big VLIW-like instruction. one of which is decrement counter and stay on the same instruction loop thing. And it's designed, it's specifically designed so that you can do the full inner loop of an FFT. But for SVP64, I decided that wasn't good enough and did the entire triple loop. So it will do an entire FFT of up to as big as you can fit into the register file. That will, so if you have 128 registers, you could probably get away with doing a 32 wide FP64 FFT and a 32 wide DCT, because you have to have the coefficients in the full set coefficient set in memory for DCT. In one of the most, it's commonly, I won't go into details. There's a heck of a lot behind that. Where would you like to get to? We want to get to a multi-core SMP high-end superscalar multi-issue out-of-order engine which knocks the stuffing out of everything on the market for performance and performance per watt. And in doing so, it does so efficiently and cleanly at the ISA level. There's one of the things we were talking with one of our developers the other day, who is a leading expert in different kinds of Symmetry architectures and vector processing, and he said AVX 512 is awful. If they'd introduced it, if Intel had introduced it before AVX 256 and all the others, AVX 2, etc., it would have been absolutely brilliant. But the fact that they didn't do so and introduced it on top of everything else, it's causing people absolute hell. And there's nothing you can do about it now that it's been added. It's quite sad, to be honest, quite alarming. You've now got thousands of instructions in the x86 ISA. We're going for around 200, 250, because we're going to be implementing scalar instructions only. Oh, and by the way, vectorizing them. Now, it's important to note that in that vectorization, as a prefix, those 200 instructions, scalar instructions, turn into approximately 1.5 million. I'll say it again. Those 200 instructions, scalar instructions, through the vector prefix of SBP64, turn into approximately 1.5 million vector instructions. So it's going to be several years before aspects of SBP64 and how powerful it is going to emerge over time. So on this basis, we want to introduce 3D GPU, video, and other accelerated tasks as first-class citizens to the Power ISA. i.e., you do not require a separate accelerated core. You'll actually be able to run a fair commercial competitive rate with what is currently done on a GPU, and also dramatically simplify the task of the software and programming task of doing so. Because at the moment it's absolute hell. I don't know if you've ever looked at the way that GPUs operate, but because you have a separate core, to keep them occupied they have tens of thousands of queues. You have inter-process communication using shared memory over PCI Express, or in the case of an embedded GPU, you have a shared memory area. And it's I/O memory mapped. The memory space of the GPU is mapped with the CPU. The result, the upshot is to keep the thing occupied and do all the work, cover the workload. You have to use remote procedure call marshalling and unmarshalling. You take your function call parameters, you squash them up into a serial stream, send them over shared memory to the GPU, get the GPU puts to shove it into the queue along with 10,000 other function calls that you happen to be that the CPU happen to do, process them, and then send the results back, notification that the results back over the marshal. Who came up with this idea? I don't know. But it means that you can have a separate product of a GPU sold and a GPU card sold alongside going into a general purpose computer. But the complexity involved is just mental. Wouldn't it be just easier if it was in the same processor? So you want your 3D instruction, right? Call it now, there and there. It's done. No context switching, nothing. So this basically will be adding floating point cosine to the power ISA. We will be adding floating point ATAN2 to the power ISA, not make it call and have to get the answer back, several microseconds later, once it's come out of a queue along with 10,000 other other tasks. Yeah, much cleaner design. So we also want to advance SP64 to include extra V, zero overhead loops, coherent graph and node processing, large matrices, and large FFT and DCT. Now this requires a little bit of explanation. SVP64 as originally designed is if you're familiar with extra V does extra V does coherent processing and obtains access to memory so that you can feed the processor from memory, where SVP64 does exactly the same thing but assumes that it's in the register file already. So where extra V works with memory, SVP64 as currently designed works with the register file. And so that's why you end up with a limit on the moment on the size of the matrices and the size of the FFT and DCT that you can cover is limited to that which in SVP64, the current version, is limited to that which you can hold in the register file at any one time. There are some workarounds around that, but they're not very good. So what I'd like to do, after discovering that there was the ETH Zurich team had created something absolutely fantastic, where they'd gone back in time, and when you refer to a particular floating point register, instead of reading it from the register file, it reads the data as if it had come from the register file, but it's actually come from some cache coherent memory, which is auto-incremented. So FP5 and FP6, when they are set into this special mode, actually use an implicit hidden load with increment. Load and increment pointer, which is the sort of thing that you used to see in the Motorola 68000 and the mini computer instruction sets, the PDP-11 historic. They've been typically been dropped now from RISC cores because they're actually really complex, but they were really necessary part of the process at the time. And as usual, things come back full circle. Now, extra V basically has a little bit more complexity in it. Is that whilst it's not just a load and increment, it's load and analyze and do a little bit of processing for basically for graph node processing so that you've got some ordering in your data and some pre-processing, but otherwise it's a coherently feeds your processor in a similar way to the etheric work, and by extension in a similar way to load with auto increment pointer. But that load with and auto increment is actually load with auto do something other processing so that the next one is loading some other thing. And because it's a deterministic path, you can actually have your caches and your memory do the loading for you, and the core knows that it's getting deterministic behavior. So it's kind of like synchronized work. And this is something that I really, really want to integrate into SVP64 to extend it beyond its current limitation of only being able to work with data that's currently in the register file. And on top of that, there's something by, I can't remember, I never remember his name, but if you look up ZOLC, Zero Overhead Loop Control, you will find some fantastic work which resulted in a massive 40% reduction in the time to complete an MP4 decode. And this was with a single issue scalar, a single issue in order core. Absolutely astounding work. Because he had nested zero overhead loops, which were able to jump about in a stack. It's absolutely incredible. It's astounding work and well worth looking up. But it turns out that SVP64 actually had to start implementing the beginnings of zero overhead loop stacks for the FFT and discrete cosine transform and the matrix multiply operations. So the similarities there were worthwhile exploring to actually include that. So basically, where we'd like to get to is to extend and supercharge Power ISA to beyond its already existing supercomputing pedigree. As you can imagine, this is a lot of work. So we've got this very, very basic, very, very basic core with plans to get to something that's just enormously ambitious, supercomputing class instruction set and processor. But it's important to know that's where we're going, because otherwise some of the decisions that we're making in design decisions that we're making just don't make any sense. So where we are now, well, we're tracking Microwatt at this early stage. We're tracking Microwatt extremely closely. And the reason is because implementing the power instruction set requires a huge amount of expertise. And in the form of the team behind Microwatt, which includes Paul Macaris, Anton Blanchard, Ben Herrem-Schmidt, Mike Newling, and Joel S. Joel Schenke. The level of expertise that team has is just phenomenal. I am always deeply in awe of their competence and knowledge. So tracking what they're doing saves a huge amount of time. But we can't use VHDL as it stands because we need to extend, as I mentioned earlier, with the dynamic SIMD. Doing that dynamic partition SIMD in VHDL will be absolute hell. And the only reason the only way we can get away with it is use an object-oriented programming language. And there are only two really good object-oriented HDL languages in common usage today. One is Chisel, and the other one is Namigen. And with Namigen just having reached number one on the TO index at 1/3 of the world's programmers, we decided to go with Python. Chisel is somewhere around 1/20th or 20 on the list. It's just you don't do that to yourself. So we currently have all three Verilator, Namigen, and Icarus Verilog simulations running, and I've just recently added to the actual Microwatt source code in a branch the ability to swap out the Microwatt core and put in a Libre-SOC core or anything else that is that wishes to comply with a wishbone interface plus the DMI interface, which is a de facto standard for debugging in RISC-V, Microwatt, and Libre-SOC, and a single external interrupt wire. And that's it. That's all you need. When you have those three things, you can drop in anything you want. You could drop in a RISC-V core. You could drop in A2O if you really wanted to. If you put in an adapter between its current interface, memory interface, and wishbone. So the Icarus Verilog simulations were quite recent. What we're doing there was cover this a bit later and a bit further down. What we're currently doing is there's a student, Jean Thomas, who did a port of light DRAM to Namigen, and he found a Micron Verilog implement model. Joined it together with the ECP5 lattice models, and with this DRAM controller that he developed, and did a cycle accurate, timing accurate simulation of the of DRAM core, of his DRAM core as a DDR3 core as a test. Now, I then used that to add the Libre-SOC core to it, so that instead of doing just wishbone reads and writes directly to the memory locations in order to initialize the DRAM and do the read and write tests, I actually ran the Microwatt cold boot memory initialization sequence as a Power ISA program emulated by Icarus Verilog. And I'm in the middle of doing that, sorting that out at the moment. So on top of this, we're also adding a new single issue in order core, which again was using the exact same pipelines that were already done and already completed from the test core. Now, these pipelines have had a wrapper put around them, which allows them to be tracked for out of order multi-issue purposes. So it's total overkill. If you think this is why it's important to understand that we're not just going for something like a goal of doing maybe an in-order core, and that would be really exciting. No, we want to go for a full monster multi-issue, out of order, super scalar, supercomputing implementation. And that means that we need, even at the low level, even when running at instruction of 0.1 instructions per clock level, we'll still have superscalar 12 separate superscalar pipelines. And it's just a matter of, over time, of upgrading one component at a time. And so our current focus is to replace the finite state machine core with a single issue in order core. But interestingly, what we will be doing is it will still be superscalar, so it will actually be capable of completing instructions out of order, and part of the job of the in-order core, ironically, will be to spot that and maintain the order. It's actually because the different pipelines complete at different times. So the multiply takes 3 cycles, logical and the ALU take 2 cycles. Div takes, I think we've joined several combinatorial blocks together, but I think it still takes something like 64 cycles to complete, or maybe 32 cycles. So everything's different, different completes at different times. So we've actually had to put in some something that looks similar to a 6600 scoreboard to track as a vector bits, a vector of register usage per pipeline, which then gets merged back. It's complicated. No, I wish we didn't have to do it, because it's actually going to take up a lot of gates. But it is what it is. Now, we're also in Verilator simulation. I've been running through the gamut of the microwatt unit tests. Now, this is in addition to the ones that we already have, because the ones in Libre-SOC are basically extremely small. It's like between 1 and maybe a maximum of 12 instructions. The average is usually about 2 instructions. Whereas the microwatt unit tests typically focus on much bigger programs. They've assumed a certain level of functionality has been achieved, and so they are basic bare metal programs. The Hello World, I think, is something like 1,800 bytes. It includes initialization of a UART 1650 and prints, hello microwatt, it works. But you have to upload that into an SRAM, a simulated SRAM, to do it, etc., etc. And that's where the microwatt mini SOC fabric comes into play. It's called soc.vhdl. If you look at the source code of it, you'll find it puts everything together. There's also an MMU test, and we pass all of the MMU unit tests. That was a lot of fun, because we didn't have some of the parts of that infrastructure in place, so it was about 4 weeks getting that thing. But it was, the whole purpose of it was to try and run it and things. So we now have a microwatt compatible level 1 Dcache, iCache, and a Radix MMU, and so those are all passing. The Zix test, actually we had running 18 months ago already. Likewise, the timer decrement unit test, the Hello World one, and we're also able to run them. Have been able to run the MicroPython one for over 18 months now. But the MMU one was the big one that was new, and it's literally been over a year's work porting that and making it and getting. I mean, we had dozens of unit tests to get that to run. So when I got that running, as I modified the microwatt unit test to be able to add in an external core, and also modified it so that it would the Verilator simulation, so that it could load memory from an external file. So rather than needing an external DRAM controller and a simulation of the same, you say, I want this entire wishbone bus, this entire SRAM, I want it to be 512 megabytes, emulated in C++. Here's the file, go. And that actually has been sufficient to actually boot Linux 5.7, the Microwatt Linux 5.7 build root. From Microwatt, it takes about 6 hours to complete. It's about 5,000 instructions a second. It's horrendously slow, but it completes and it gets to the prompt, and then you type return, and 30 seconds later you get a root prompt, and you type ls, and it's awful. It's like, it's so slow. It's, the 30-second response time to pressing keys, but it works, and that's absolutely brilliant. I got to 20 hours runtime on that after fixing a huge number of instructions, because after having the MMU work, it still wasn't enough. And even more stuff to fix. I got to about 40 lines through the Linux kernel log files at 20 hours and decided I had enough, and decided to move on to FPGAs. So now we've been able to run without the MMU. We've been able to run on the Versa ECP5 for about 15 months now. I've confirmed that that's now running on the with the MMU is running on the Versa ECP5. I've also managed to boot on the ULX3S, which is and that was only 12 megahertz. The Versa ECP5 we can manage 55 megahertz, which means hooray, we can actually initialize the DRAM, the DDR3 memory on the Versa EP5, and we should be able to run Linux on it fairly shortly. The ULX3S only achieves, which is a larger FPGA. The next PNR ECB5 doesn't cope with the amount of routing that's involved, and the maximum clock rate at the moment is only about 12.5 megahertz. But because it is a ULX3S, uses SDRAM, that SDRAM will run at that very low speed, so it's okay. The next two things to do on the to-do list, I have an RTA7100T from Digilent, which is an awesome piece of kit. It's got a huge number of interfaces, and you can get PMODs for VGA things. It's really good. And I also want to get it running on the Orange Crab, which is another Versa, which is another ECB5 85K thing. Now, if you're going to get any of these FPGAs, for goodness sake, don't get anything below 85K LUT4s. You will not be able to you run. If you're extremely lucky, you will fit into an A735T, but I don't recommend trying it. Go for the larger ones, for goodness sake. We've also we're creating a Namigen-based peripheral fabric. Now, what a peripheral fabric is basically you've got your core, but you don't have it connected to anything. And this is one of the things that puzzles people who are familiar with, say, for example, x86 with Northbridge and Southbridge. Who think, well, if you finish the core, that's it, isn't it? That's all you need. Well, no, you need peripherals. You need a memory controller, and you need a connection between the core and the memory controller. And then you add, say, an Ethernet peripheral. You want an Ethernet peripheral, and well, now you've got two peripherals. You have your memory and you have Ethernet. Well, which one gets priority? So now you have to have an arbiter which splits the data, but splits memory requests between the two, tells and so on and so forth. And what address do you want them at? What address do you want your Ethernet peripheral to be at? What address do you want your DRAM controller to be at? How big is it? Does it generate interrupts? If so, do you need to feed those interrupts back? And once you get into it, it's actually a hell of a lot more than you think. You've done your core, and that's great, and it should be everything that you need. Well, no, actually, in the peripheral fabric is almost as much development, design and development as went into your processor. And particularly when you're doing an SoC, you can have 1,000 pins worth of functions that need mapping. You can have 100 interrupt lines that need funneling down to that one interrupt on your core, external interrupt. So now you need a Zix controller. right? Or in RISC-V, that's a PLIC, or more recently a CLIC, where it's the CLIC that you connect, or the ZIX controller that you connect to that one interrupt, one external interrupt line. And then when you get the interrupt, the interrupt handler will go. The very first thing it will do is query the ZIX controller. Hey man, what did you do? What interrupted me? What's peripheral? At what priority wanted my attention? Was it the open cores? Was it the UART? Was it the I2C? No. Was it the SPI? No. Thing. And you go through and enumerate all of the different peripherals and service the interrupts. So it's this funnel, but the peripheral fabric hangs all of that together so that as an SoC designer, you don't have to reinvent the wheel every single time you just want to deliver a customer product. All right. And so that's what that's about. Now, what we've specifically been doing is to integrate JTAG boundary scan and a PinMux into the peripheral fabric. Okay, and will also be designed for test. Now, going to the significance of that. Right. The majority of open hardware development has been on FPGAs up until this point. And if you look at it, if you want to repurpose an FPGA's pins, so you want the pins that were previously used for I2C, you want to use them for a UART instead. Well, you just rebuild the bit stream for your FPGA and upload it and go. Right? You don't need a PinMux, whereas an ASIC, once you've put it into silicon, you've paid your $250,000 for 45 nanometer, or your 1 million for 28 nanometer, or your $16 million for your 7 nanometer masks. The last thing you want to do is to say, oh, by the way, if you want to use a UART instead of an I2C, you're going to have to buy another chip. Absolutely last thing you want your customers to do. So what you do is you put those 1,000 or 2,000 pins worth of peripherals through a pin multiplexer, as I'll call it, PinMux, out to 200 or 300 pins. And what that does is it saves an awful lot of money on packaging and makes the package more reliable. You get much higher yields. So, but now you've got some complexity in there that you've actually got to test all those pins and the peripherals, and that's what we will be doing with the JTAG boundary scan. Just in case one thing doesn't work, we're actually going to integrate the PinMux into the JTAG boundary scan so that you can, over the JTAG interface, you can tell the PinMux that you want to connect the I2C device to pins X5, and then next you want X5 to connect to the UART transmit line. Right. So that's doing. It's quite innovative. Now there are a couple of efforts, prior efforts to do this. I developed one for IIT Madras for the Shakti core. When was that? It was 2 years ago now, and it was in BlueSpec. Sorry, it was written in Python, but it generated BlueSpec, and the technique that I used was very similar to that which I've used for web development of web pages. So rather than the outputting HTML, and constructing a complex chain of HTML from a database. My database was a CSV file containing the specification that was needed. This pin pin A5 must map to I2C, a GPIO5, UART transmit, and SPI zeros Mosey line things, and it would generate the code for that, the HDL for that. But it also generate the interrupt lines and connect all of those up automatically, and so on and so forth. But it would, instead of outputting HTML and CSS, it would output .bsv, multiple .bsv files from, interestingly, templates, exactly as how you would do HTML and CSS. Right? It became very difficult because I ended up with about 5 levels deep of coding of loop upon loop upon loop upon loop, which were construct code fragments that were handed up to higher level functions, that eventually the last one was write this entire lot to a file. Very, very difficult to understand. Right? It worked, it did the job. The documentation is meticulous and detailed, and if I was to go back to it, I would have, as the author, I would have enormous difficulty understanding it and following what I'd done. It's always a bad sign when you don't understand something that you yourself has written. Now, the other one that after I posted that on the RISC-V mailing list, the low risk team picked it up and reproduced the concept in something called OpenTitan, and they called it Earl Grey. So they did the similar trick, but in this case, what they did was they used the PHP style. It's exactly the same problem. You have to have a template file into which contains the start of your Verilog source code and the end of your Verilog source code for your peripheral fabric of your module, into which you're going to substitute the peripherals and the interrupts and all this and the dressing and everything and the arbiters and the decoders and everything. You can wire it all up. And they decided to use Python Ginger, which is commonly used. It's very, very commonly used in Django, but it's equivalent to Zope, if you remember Zope, and it's equivalent to PHP. And again, I just looked at it and my heart sank as I knew how much work had gone into it and how unmaintainable it would be. Sigh. So from these lessons, it's only when you've gone through this kind of hell that you decide to do something different. What we decided to do was to use Python Namigen. So you dynamically construct the HDL there and then. You use Python-based classes and leverage the object-oriented nature of things. So rather than outputting Verilog using text file templates, you use the power of Namigen which already exists to output the HDL. And the nice thing is that if designed well, you can use object-oriented abstractions and techniques which are well known in compiler development and AS tree node walking, to do something different as well. So for example, once you've got your walker of the CSV files, which contains all the information about what you want, you can tell it, well, I don't want HDL generated, I'd like a Linux kernel header file generated, please. And you give it a class which it has the things. If you have a look at the way that Python itself works, you will find these walkers. If you look particularly at the libxml XML parsers, they have these on start of tag thing, on this attribute this, and on end of attribute, and and it's these abstract syntax tree AST walkers. And so that's what I would like to ultimately do, is to create this fabric where we can auto-generate, just like in R Grey, which was inspired by the work that I did on for the IoT Madras, to auto-generate the device tree file, auto-generate the documentation, auto-generate the technical reference manual, auto-generate the Linux kernel header files, so you do not have to go and write those. And you'll find that part of this is already done in LiteX, but it's done in a way that, because it uses MeGen and it uses wildcard imports, it's almost impossible for anybody to understand except for the actual developers who created it. So some care has to be taken in the development of these code bases to use strictly stick to known development techniques learned from the lessons of open source and from Python, to make sure that this stuff is actually maintainable. And that is part of our remit under the NLNet funding, is to take that responsibility seriously. So one of the other things that we've got doing is we're going to be doing a new power instruction set simulator, power ISA simulator. And that is already underway partly. And it's going to be a power ISA port of KavaTools. KavaTools is a stunning simulator which can do symmetric multiprocessing, emulation of symmetric multiprocessing using your main cores. So if you want to do 20-way SMP and you have 20 cores on your system, that your host system, each of those 20 cores will be simulated cores will be allocated to one of your host processors. And there's some very interesting tricks that KavaTools has done to achieve 1/3. This is incredible. It achieves 1/3 of execution speed of the host native clock rate. 1/3 of the host native clock rate, whilst also being cycle accurate to the hardware. I mean, it's astounding work. It's by Peter Su, I mentioned previously. He was the architect back in 1994 of the MIPS R8000. So a power ISA port to this will be extremely important. Now, bear in mind, QEMU, you will have heard, can achieve similar levels of performance, but it does so by doing just-in-time translation, which severely handicaps your ability to do cycle accurate, hardware level cycle accurate simulation, because you're not running, you think you're running LWZCIX, and you're actually running a series of x86 instructions, about 3 or 4 x86 instructions, which have been just-in-time translated. You want to do an interrupt, you want a single step through that. Well, you're stuffed. It's really difficult. So the cycle accuracy includes things like how long do you want the level 1 cache to pretend to be? Access to the level 1 cache. If there is a cache miss, how many cycles do you want to stall for in the processing? And these are parameter options to the KavaTools simulator. So you can actually check when you're adding your new instructions, emulation of new instructions, you can compile up your programs, run them at pretty much real-time speed, give or take, give or take, and then you can do you can get real-time annotation to show you the Carver Tools inspector will show you where the inner loops are stalling, and where you haven't got pipeline access or registers or whatever it is, that etc., that are not enough allocation of registers. It's a fascinating design that hugely saves on development. It was a fascinating talk given at ISAConf 2021 last year, which is well worth looking at. But we want to add, as I said, we want to do a Power ISA port of that, and we've got €50,000 in grant funding from NNL to do that. And then once we've got the basic scalar instructions on that, we'll add SV64 on top, and then see, create a base machine profile, which and try to experiment with different profiles and see how things go. So that's where we are. Now we have quite a lot of funding. We've got some of the timescales thing. We do need help. There is money available to fund it. So if you want to help with this, you can actually get paid to do things. So we have €200,000 from Engine Pointer. The deadline for completion of that task is October 1st, 22. There is about €250,000 from LRNet, which has a deadline of October, again, same deadline. That was because it's under the Horizon 2020 program, which was extended because of the pandemic. It should have finished several months ago, but it has been extended. And under the NLNet Assure program, we have €150,000, including for the Carver Tools grant, for draft crypto primitives, bit manipulation instructions to be added to the Scalar Power ISA instruction set for cryptographic experimentation. And there's another one for Coriolis 2. So if you're interested in doing VLSI development and would like to help with that, then there's money available to advance Coriolis 2 to at least 1/1 at 130 nanometer, and to just have some performance improvements on it. Everything we do in Libre-SOC is Libre licensed. Our default license is LGPLv3 plus. If we contribute to other projects, obviously we respect their licenses, use their licenses. But default for our own code is LGPLv3 plus. And it's all available starting at https://libresoc.org. So thank you very much. With mailing list, which you're welcome to join, list.libresoc.org. We have an IRC channel on Libre #LibreSoc, which the OpenPOWER Foundation very kindly bridges over to the Matmos chat. Thank you to Toshan Bhavani for arranging that. And if you're interested in what the NLNet funding gives us and how that works, we have an FAQ. Thank you very much. Any questions?